This is the fourth and last lecture from Chapter 18 about electrochemistry, and this lecture will be about electrolysis. And electrolysis refers to electrochemical reactions that are non-spontaneous. So far in this chapter, we've talked about spontaneous cells, also known as voltaic cells or galvanic cells. So let me give you a brief introduction of a comparison of voltaic or spontaneous versus electrolytic cells. First of all, the little mnemonics we've learned that an ox chased a red cat still holds true. Oxidation still occurs at the anode in the electrolytic cell. Reduction still occurs at the cathode. In a spontaneous cell, of course, the E cell value, the voltage for the standard cell, is always a positive value. And the electrons start from the anode in a spontaneous cell. Remember, A goes to C, anode to cathode. In an electrolytic or non-spontaneous cell, you need an external power source, aka electricity. So that power source actually draws electrons from the anode, so you can kind of still think of them as starting from the anode, but they're not being given away. They're being drawn out by the power source and excuse me, and then pushed toward the cathode. So take a look at the key difference between a voltaic or spontaneous cell and an electrolytic or non-spontaneous cell. This is a really good example, I think, because it's the same overall reaction. In a spontaneous cell, you want an overall positive voltage, and if you wrote out the balanced reaction for this spontaneous cell, it would look like this. Okay? Now, an electrolytic cell, which is non-spontaneous, simply flips the spontaneous reaction. So what's going on in this non-spontaneous cell is the following. Okay? And the overall voltage would be a negative value, so this is the amount of voltage that must be added to the cell in order to get this non-spontaneous reaction to occur. But if you were to calculate the E cell standard voltage for this, it would be minus 1.10 volts. Why would anybody want to use a non-spontaneous cell? Why do you want to put energy into something? The industrial uses for an electrolytic cell typically involve the breaking apart of a melted ionic compound. We call that molten. So, for example, you might take sodium chloride, which in its standard state is a solid, apply lots of energy, and then you would get the molten sodium chloride. And now ionic compounds melt like in the thousands of degrees Celsius, so really high temperatures. But the molten form will then undergo electrolysis and provide us with some useful products, as you will see. Another key difference in an electrolytic cell is the electrodes, rather than participating in the reaction, are usually inert. That means unreactive. So a real common electrode in an electrolysis reaction is platinum. That's a metal that's very stable, very unreactive. And so really the electrode simply serves kind of as a vehicle in an electrolytic cell rather than as a reactant. But as I said, most of the time it's molten ionic compounds, molten salts. And so then you have sodium ions and chloride anions. So typically when you supply enough energy to a molten salt, what happens is the metal cations become metal, pure metal, and the nonmetal anions become the neutral nonmetal. It is this metal substance that we make that's very useful. I don't know if you've ever heard of electroplating, but there are actually these kind of spray ones, and they spray liquid metal to, like, over a car or something that you want to give a new fine metal coating to. And so that's a real common application of electrolytic cells. Here's a diagram of a molten sodium chloride electrolytic cell. And so again, instead of a voltmeter, you actually have a battery or source of electricity here. And it is pulling electrons from the anode, okay, and then pushing electrons to the cathode. So what happens then is the chloride ion gets attracted to the anode, because remember, electrons are being pulled away from the anode, so it is building up some positive charge. So the anions are being attracted to the anode, anions to anode, and where they are being oxidized, so NOx, still the same, oxidation occurs at the anode. And when chloride is oxidized, it makes molecular chlorine in the standard state, okay? And over at the cathode, where electrons are being pushed down into, so it's building up a negative charge, the sodium cations or metal cations are being attracted to the cathode and undergoing reduction. So reduction means gain electrons, right? So you're making the neutral metal at the cathode. Notice that these two half cells are connected. There's quite often some type of a filter or diaphragm system in between the two cells, but there doesn't, half cells, but there doesn't need to be. So electrolytic cell doesn't need to be, well, actually can't be completely separated, because you have a single substance, sodium chloride or some type of salt, that the components are going two different ways. So it needs to be in one big vat, one big container. Sometimes electrolysis reactions occur in aqueous solutions. And so I'm going to show you what happens when you add electrical energy to water, because in some cases the water will actually undergo an electrochemical reaction rather than the salt that you have dissolved in it. So that's a big consideration for electrolysis. When you electrolyze water, when you add electricity to water, you generate the components of water, in other words, hydrogen gas and oxygen gas. There. And one at each electrode. So at the anode, remember, oxidation occurs at the anode, which means the substance has given away electrons. Reduction occurs at the cathode, which means the substance has accepted electrons. If you look in the standard reduction table, any standard reduction table, you will see these two half reactions for water. So the bottom line is water can undergo oxidation or reduction depending on whether, depending on the conditions it's under. And so if you were to add these two half reactions together, you would actually get what I've written here. Okay. Now, as I said before, if a salt like sodium chloride is dissolved in water rather than melted in a pure form, then you have three substances. Well, you have both the cation and anion present, but you also have water molecules present. So when you're trying to decide what the products are going to be at the cathode and anode, you need to consider all of these components. And whichever component is easier to oxidize or reduce will be the one that does so. And so let's look at an example. So that probably doesn't make sense. This is the type of rationale you go through with an electrolytic cell. We have aqueous NaCl, which means these are the components we have to look at. We have sodium cations, chloride anions, and water molecules. So you need to look up the oxidation potential for all of these and the reduction potential for all of them. The one that is the most positive value will be the one that's oxidized. The one that's the most positive reduction value will be the one that's reduced. So let's just look at that. Let's look at oxidation first. Okay, oxidation means losing electrons. A cation is not readily oxidized. It's already lost an electron. It is not going to lose any more. So if you're looking for oxidation, you want to look at the anion and water molecule. Those are the two you're comparing. If chloride anion is oxidized, it makes neutral chlorine. If a water molecule is oxidized, and you probably won't be able to memorize this half reaction, but it's always written out in the standard reduction table. But if water is oxidized, this is the product. And so you look at the two oxidation reactions and which one is most positive or which one is least negative. It would be water, okay? And so water would be oxidized preferentially over chloride ion. Okay, so the chloride won't happen in this situation. So let's look at the reduction half reaction possibilities. Reduction, of course, means addition of electrons. So the chloride ion, it already has an extra electron, so it's not going to participate in a reduction. That's pretty safe. But the cation could undergo reduction, or again, water could undergo reduction. So look up the reduction cell potentials for each of these. The one that is the most positive, negative 0.83, one that requires the least amount of energy will happen, and that's reduction of water. So what do we have? If we build an electrolytic cell with NaCl and water, nothing is going to happen to the NaCl at all. The water will be preferentially oxidized and reduced, and nothing will happen to the salt. Not very useful, is it? Here's one I want you to give a try with a little bit of guidance from me. Let's say we do an electrolysis reaction of an aqueous. Make sure you read carefully to know whether it's molten, which means pure melted, or aqueous of sodium iodide. All right, so what do we have present? We have the sodium ion, cation again, we have the iodine anion, and we have water molecules. So think of the possible oxidations. I've given them here, which I normally won't in a test, and here are the possible reductions. You've got to decide which one of the oxidations will occur and which one of the reductions will occur, and see if you can write a complete reaction for that. And I would recommend putting the video on pause, trying to work it yourself, and then checking your answer on the next page. Okay, hopefully you looked in a standard reduction table and wrote down the oxidation values. Now remember, if you're looking in a standard reduction table, you need to change the signs of the oxidation half reactions. Don't forget to do that. And so the iodide ion will undergo preferential oxidation because it requires less energy to do so. So it'll get preferentially oxidized over water. Looking at the reduction, and this is something you just may want to memorize. Anytime you have the sodium cation, water is going to be what's preferentially reduced. So the reduction of a water molecule costs less energy than the reduction of sodium. And so what do we have? We have our oxidation half reaction is the iodine. Our reduction half reaction is water. So hopefully see if you can combine those two as well as the voltage, and that would answer the question. So the standard cell voltage for this electrolytic cell is minus 0.95 volts. And that's what you expect for electrolytic cell, the minus sign. And the overall reaction, I'm hoping you got that right, is shown right here. And it looks like it did not fix my subscripts, but I think you can still read it. So that would be a very typical question to ask about electrolytic cells. There's one final type of problem you need to do with electrolysis, and it's really a unit cancellation type problem. You can actually calculate how much product can be made depending on how many electrons are transferred or what current you applied to the electrolytic cell. It really is dimensional analysis. All right, so the things you need to know before we get started: Faraday's constant, which I will always give to you. You'll have to use that in these calculations. And 1 amp, this is something I won't give you. You need to remember that when somebody says 1 amp, what they're really saying, an amp is coulombs per second. Okay, so it's the amount of charge per second. Here's a very typical electrolytic cell problem that asks you to calculate how much neutral metal you could generate. This question is saying calculate the mass, which is typical, of copper. I just put the 0 here. I'm talking about neutral copper, copper metal, okay? How much of that is generated when 0.4 amps of electricity, obviously, is passed through a copper ion solution for 25 minutes. So my first hint to you here is always start with amp. It's going to be a big unit cancellation. So 0.400 amp. Remember what I told you an amp is? It's the first thing I do. An amp is coulombs per second. And now whatever's on the bottom in your units, you want to get rid of it. So we're dealing in seconds and our time is in minutes, so we're going to have to convert 25 minutes to second. So we know that there are 60 seconds in 1 minute, and that we supplied this current for 25 minutes. So let's see what all we can cross out. Seconds crosses out, minutes crosses out, and when we do this, we should figure out how many coulombs we have. So 0.400 times 60 times 25 will give us the amount of coulombs or charge that we have delivered to this solution. And that number happens to be 600 coulombs. Okay, we need to get now from coulombs is the first step, and the second step is to get to grams, from coulombs to grams. So if we have 600 coulombs, now you use Faraday's constant. We haven't really talked about the units for Faraday's constant, but basically what it tells us is that there are 96,500 coulombs of charge in 1 mole of electrons. Okay, so there go our coulombs. Now you're in mole of electrons. We need to get our way over to copper, however. So we want to relate moles of electrons, and we're trying to get the copper, to moles of copper metal. Okay, and where do you get that ratio? You have to look at the balanced reaction. So let me write that here. So if we take copper cation, how many electrons does it take to get it to make 1 mole of copper, neutral copper metal? Okay, it takes 2 electrons to make 1 mole. So that's our mole ratio. 2 electrons make 1 mole of copper. Mole of electrons goes. And now simply the molar mass of copper to get to grams of copper. And the molar mass of copper is 63.55 grams in 1 mole of copper metal. And so if I do all this math, I get as my final answer 0.198 grams of copper metal is produced. And that's it. So that's going to take some practice. I would recommend doing a few of those problems to get used to it. Here's one for you to try. Very similar problem. It's asking for the mass of silver. Okay, so neutral silver metal again. And you're starting with 0.250 amps. And silver nitrate, you need to know the formula. Silver, by the way, in a salt always has a charge of +1. You'll need that so that you can figure out how many electrons are transferred. And 90 minutes is your time. Okay, remember, always start with amps, and remember what amps is equal to, coulombs per second. So I would suggest pausing the video, see if you can do it yourself. The answer to this is 1.51 grams. So how'd you do? I worked it out right here if you need to check yourself. But remember, you start with amps, convert seconds to minutes, and your intermediate is you have 1,350 coulombs. Use Faraday's constant to convert coulombs to moles of electrons. The mole ratio of electrons to silver you get by writing out the balanced half reaction. 1 mole of electrons gives 1 mole of silver, and the molar mass of silver is 107.87. When you do that math, you find that you can produce 1.51 grams of silver. At the end of every chapter, they have this giant concept map, and I thought this one was actually kind of useful for at a glance, what have we covered? First of all, oxidation reduction, you need to assign oxidation numbers, identify the half reactions, and create balanced redox reactions. Then we looked at voltaic cells, which are spontaneous, and we learned that we have an anode and cathode. We learned the relationship and formulas that relate voltage to free energy and to the equilibrium constant. We use the Nernst equation to calculate E cell that are not under non-standard conditions. And then just in this lecture, electrolytic cells, which are non-spontaneous cell, we learned how to do the calculations to calculate how much metal we can make using the Faraday constant. And that we, through electrolysis, we can do electroplating of thin coatings of metal. So anyway, it's kind of a nice at-a-glance review. That's it for Chapter 18. That's actually it for new material for Chem 2.